All right, folks. Well, welcome back. I hope everyone had a good weekend. You're able to get some rest and stay away from the computer and screens for a little bit and try to enjoy what you could about of the weekend. Okay, but let's continue on with where we left off with last week, and that is interpreting these chemical equations. Okay, so what I would like to do to start out this morning then is have you take a look at these two equations here, check to make sure that they are balanced. Okay, and so this is number 6 in your problem set, and what I'd like you to do is take these two equations here, take these two equations, and what I would like you to do is to interpret them in terms of moles. Okay, and in terms of atoms and molecules. Do not worry. So don't do masses yet. We'll do that next. Okay, do that next. But do interpret this in terms of atoms, molecules, and then we'll talk about the moles as well. Okay, so go ahead, take about a couple of minutes to get this done, and then we'll go over it together. Okay, go ahead and get it done. All right, let's go ahead then. Let's take a look at this here. And what I'd like to do then is I'm going to go ahead and take a look at each equation at a time. Okay, and what I'd like to go over with you then is let's go ahead and start out with atoms first. Okay? The balanced equation, and so make sure you count and make sure that everything is balanced first of all. And so 2, 2, 1, 2 will balance everything out. Okay, so let's go ahead and let's count atoms first. And so when we count atoms, we're looking at the individual atoms on both sides of the arrow here, and we're just going to count them. So let's start out with hydrogen here. Okay, so hydrogen. Okay. And so with the molecule here, which is H2SO4, don't worry about the coefficient right now. Let's ignore that just for a moment. H2SO4, in this one molecule here, we have 2 hydrogen atoms. Okay, so 2 hydrogen atoms in one particle of H2SO4. But from the balanced equation, we were told then that we have two molecules of H2SO4. So that means then we will have a total of 4 atoms of hydrogen in this one molecule here. Okay, so that's what we start out with. So same thing with sulfur then. In one molecule of H2SO4, we have 1 atom of sulfur, but since we have 2, the coefficient tells us we have 2 of these here, we will have then 2 atoms of sulfur. And then with oxygen, then we have 8. And so if you notice here, what we do is we take each one of the subscripts and we just double it. We double it, okay? So we double it here, we double it here, and we double it here. That's where we have our atoms, okay? And so with that said then, we have then a total of 14 atoms on the left-hand side, okay? Let's go ahead and do the same thing on the right-hand side. Okay, so we're going to count atoms first of all, starting with hydrogen. Okay, so here with hydrogen, we have in one molecule of water, we have 2 hydrogen atoms. Okay, but since we have 2 hydrogen water molecules here, we have a total of 4 hydrogen atoms. Okay, let's go ahead then. Let's count sulfur next. Okay, sulfur is right here. Okay, in one molecule of sulfur dioxide, we have 1 sulfur atom. Since we have 2 sulfur dioxide molecules, we should end up with 2 sulfur atoms as well. Okay. Now the last thing is let's go ahead and count oxygens. Okay. So here in one water molecule we have 1 oxygen atom. In 2 water molecules we'll have 2 here, 2 here, and 4 here. So we have a total of 8 oxygen atoms as well. So when you total up the atoms here, you also have 14 atoms of on the product side. So the number of atoms you start out with and the number of atoms you end up with are exactly the same, which is what we expect. So therefore, atoms are conserved. That means then we will have the same number of atoms on both sides. So atoms are conserved. Okay. All right, let's go ahead and count molecules now. Now, when we count molecules, and we're counting the total particle. Okay. Sorry, let me go ahead and restart really quickly. Particles. Okay. Okay, total particle. Okay, so that means then we're counting the whole thing. We're not breaking it up into individual atoms. We're counting the whole thing. So with that said, then this is the molecule. This is the complete particle to start out with, and we have two of these to start out with. We have 2 on the reactant side. Okay, so we have 2 total particles to start out with. Okay, so let's go ahead then and let's count the right hand side. So we have 2 waters from the balance from the coefficients here. We have 1 oxygen, and we have 2 sulfur dioxides, which means then we have 4 total particles. Okay, and if you notice here, the number of particles do not equal one another, and so the number of atoms should always equal, the number of particles do not. Okay, so make sure you keep that in mind, that atoms are conserved. Okay, so let's go ahead and highlight this here really quickly. I want to make sure everyone's clear on this. Atoms are conserved when it comes to conservation, but molecules are not. Okay, so make sure you keep that in mind as we move forward. Okay, all right, let's go ahead and do the next one. Let's go ahead and do the next one, and let's do the same thing. Okay, I'm sorry, let's do moles first. I'm sorry, before we go on, let's count moles. Okay, so I forgot about that. Okay. All right, so with that said then, let me just include here really quickly. Okay, so instead of just counting individual molecules, now let's count moles. So the coefficient also tells us the number of moles of each substance in our reaction here. So instead of having just 2 molecules of sulfuric acid, we can have 2 moles as well. Okay, same thing here with water. We would have then 2, and I'm sorry, this should be moles. So we're counting moles now. 2 moles of water, 1 mole of oxygen, and 2 moles of sulfur dioxide. Okay, so for a total of 5, I'm sorry, I miscounted the last one. So 5 total moles. Okay, and here we have only 2 total moles. And if you notice that they're not equal either. Okay. All right, so with that said then, make sure you keep that in mind, and let's go ahead and let's do the next one, and let's see what we get. Okay. Okay, let's go ahead and count the atoms, molecules, and moles. So I'll go ahead and write moles in there in just a moment. Let's go ahead and count atoms, molecules, and moles really quickly. Okay, go ahead then and count atoms first. Okay, so we have 2 atoms of aluminum from here. We'll have 6 total atoms of hydrogen. We have 3 atoms of sulfur, and then 12 atoms of oxygen. Okay, so we're counting individual atoms here. So we're taking each one of these particles, these molecules, and breaking them up and counting individual atoms. And if you do so, then let's hopefully you recognize then that we have it's 18, 23 total atoms on the reactant side. Okay, so let's go ahead and let's look at the product side. So we have then aluminums. If the equation balances correctly, we find aluminums here. We get a subscript here. The coefficient is 1, so we're going to have 2 atoms of aluminum. Hydrogen, it's found right here. 1 hydrogen molecule is 2 atoms combined together. If we have 3 of them, we'll have a total of 6 hydrogen atoms. Okay, let's take a look at sulfur. Sulfur then is part of the sulfate anion here. Okay, and it's in parentheses. So in 1 sulfate, you have 1 sulfur atom, but you have 3 of these here, and 1 here. So 3 of these, which gives us 3 sulfur atoms. And then finally with the oxygens, okay, we have 4 in 1 sulfate. We have 3 of these in 1 of these aluminum sulfate particles. So therefore, we also have 12. Okay. So again, if we add these up here, we'll have then 1823 total atoms as well. Okay, and we see then that those should be equal because atoms are conserved. And I want you to keep remembering this, folks, because this will come up again and again. So atoms are conserved, and we see that here. We start out with 23 total atoms. You end up with 23 total atoms. Not only are the numbers the same, but the types are the same as well. Okay. All right, let's go ahead and let's count the particles then. So we're going to count total particles. We're going to count the particles as a whole this time. Okay, so we have 2 particles of aluminum. Okay, so we have 2 aluminum particles. And you want to consider it so we can put molecules in quotes. Okay, so we have 2 molecules of aluminum. Remember, you can use that term generically to indicate number of particles. And therefore, then combined to that, we have 3 particles of H2SO4, sulfuric acid, on the reactant side. If that's the case, then we'll have 3 hydrogen particles and 1 aluminum sulfate particle. And if you notice here, we're no longer counting individual atoms. I mean, though technically these are atoms here. We're doing the same thing, and we're counting them as total particles. The aluminums on the left-hand side represents then individual particles as well. Okay. All right. So let's total it up here. We have then 5 total particles. Okay. And on this side here, we have 4 total particles. Okay. And if you notice here, the number of particles do not necessarily have to be equal. Now, could they be equal sometimes? Absolutely, but they don't have to be. Okay. All right. So good. Let me go ahead. Let's count moles. Okay. And let's go ahead then and take a look. So let's go ahead and count moles now. Okay. So okay. So on the left-hand side, then we have, instead of 2 molecules of aluminum, we have 2 moles of aluminum and 3 moles of H2SO4, which gives us a total of 5 moles. Okay, on the left-hand side, doing the same thing here, we'll have 3 moles of hydrogen and 1 mole of aluminum sulfate, for a total then of 4 moles total. So we have 5 moles total, 5 total moles, and 4 total moles on the right, on the reactants, the product side. And again, those are not equal. Okay? So hopefully you should be able to do that, folks. Remember, atoms should, when you're counting atoms from the information given to you in the balance equation, the number of atoms should always be the same on both sides of the arrow. The number of particles, that is molecules, and the number of moles should not be the same. Of the 3 that we're counting here, the number of moles, and it's going to be important because we did this. So let's continue on then, folks. Okay? Let's take a look at what we have here. Okay? So we've left off the discussion of moles on Friday, and we talked about how the number of moles corresponds to a certain number of atoms, certain number of particles. So you can imagine this here. If we do this equation here again, let's go ahead and take a look at this equation. If you take a look at it, okay. The balance equation here gives us a balance equation of 1, 3, 2, which means that we have 1 mole. So this represents 1 mole. Okay, and that's we have here of ammonia, nitrogen, 3 moles of hydrogen, and 2 moles of ammonia. Okay, and that's what I have written here for you as well. So we have then each, if we have this many particles of each, that's what we have here. Okay. But I asked you, and so you get a ratio here of 1, 3, 2. So make sure you keep that in mind as we move forward. You have a 1, 3, 2 mole ratio. And so as we move forward then, let's go ahead. What I asked you to do on Friday was I asked you to do these calculations here. So go ahead and get those out. Okay? And let's take a look at them. And let's do this calculation right here. Let's do it together. Okay? And you can compare your answers. Let's go ahead. All right, so make sure you keep in mind though, we have a 1, 3, 2 mole ratio here. We'll get to that in just a moment. Let's go ahead and do this calculation here. So we want 1 mole. So this conversion then is a moles to mass conversion. We have 1 mole of nitrogen. Okay. We want the grams of nitrogen. So therefore then we want the mole ratio, molar mass. Okay, the molar mass here is going to be 28 grams, sorry. 28 grams of nitrogen for every 1 mole of N2. So therefore, then 1 mole is going to correspond to 28 grams of nitrogen. Okay, let's do the same thing for hydrogen here. So we have 3 moles of hydrogen. That will correspond to, we want to find then the mass of hydrogen equivalent to that. Okay, and so use again molar mass here. It's going to be 2 grams of hydrogen for every 1 mole hydrogen. So therefore we have then 6 grams of hydrogen. Let's do the last one, ammonia. We have 2 moles of NH3. Okay, we want to find the mass of NH3. Okay, and so with that said, then let's go ahead and plug in the molar mass of 1 ammonia, which is 17 grams of ammonia for every 1 mole of ammonia. Okay, and so we end up here with 34 grams of ammonia. Okay, all right. So what we have here, let's go ahead and take a look at this then. Okay, what we have here then are the masses that are equivalent to these amounts here. Okay, so if we started out with 1 mole we start out with 1 mole nitrogen. The amount of the mass of nitrogen equivalent to that would be then 28 grams. Okay, if we started out with 3 moles of hydrogen, the equivalent mass would be 6 grams. And for I'm sorry, 6 grams. Let me go ahead and erase these here. We already have that. Sorry. Go ahead and erase these. Okay. Okay. 6 grams of hydrogen, and then for ammonia we have 34. Okay. All right, so if you want to do the mole ratio here, let's go ahead. The mole ratio is 1:3:2. That is the ratio of moles here. Let's do the ratio of nitrogen, hydrogen, and ammonia here. If we do that, if we reduce that, remember we want to make sure we reduce that, we get then a 14:3:17 ratio. Okay, so we get a ratio here that is, this is the mass ratio. Okay, so let's compare here. This is going to be the mass ratio. That's the ratio of the masses. This is the mass ratio. Okay, and if you notice, mass ratio and the mole ratio are not the same. They are not the same, and we do not expect them to be the same, and they should not be the same. Okay. However, so make sure you keep that in mind. This is our mole ratio. We get that directly from the balance equation. Remember the balance equation we saw then in the previous slide is a 1:3:2 mole ratio between nitrogen, hydrogen, and ammonia. This is the mass ratio here, and if you notice, they are not the same. And the reason why I want to point this out to you is that when we deal with stoichiometry, the coefficients tells us the number of moles, the relative number of moles of the components of reaction, not the masses. And that's what I want to point out to you. So this we obtain from the balanced equation. This, the mole ratio we can get from the balanced equation. Okay, we can get that directly from the balanced equation. We cannot get the mass ratio from the balanced equation. These masses, and so how do we obtain masses? Because understand this, folks. If we want to run this reaction, we cannot measure out moles. We can't measure out 1 mole of nitrogen. We can't measure out 3 moles of hydrogen. We cannot measure out 2 moles of ammonia. There are no instruments, there are no tools that we can use to measure out moles. However, we do have devices that we can use, tools that we can use to measure out masses. We can weigh out 28 grams. I mean, it'll be a little more difficult, but we can weigh these out. We can weigh out 28 grams of nitrogen. We can weigh out 6 grams of hydrogen. We can weigh out 34 grams of ammonia. Now, that wouldn't be the most effective and most efficient way to do it. We'd probably measure out volumes instead, which I'll talk about in just a moment. But this tells us then what we've done here is we've gone from a unit that we don't have a way of measuring out. Now we can measure out these units. Okay? And so in order to run this reaction, then you can imagine this. In order to run this reaction, let's go ahead and write this down again really quickly. Okay, so this is the reaction itself, okay, which forms then 2 moles of nitrogen. What we would do then is we would take 28 grams, okay, we'd measure out 28 grams of nitrogen, we'd measure out 6 grams of hydrogen, and if we mix it together and everything else runs out well, we should end up with 34 grams of ammonia. That's what we have here. Okay, and if you notice something here, folks, add this up here, add up the masses. We have 34 grams total on the left-hand side. That equals the 34 grams that we have on the right-hand side. So like we said there, atoms are conserved, but also mass now is conserved as well. So in a balanced equation, what we're going to see then is that the number of atoms will be conserved, and the mass will also be conserved. Those two will be conserved. Okay? All right, very good. Let's go ahead then and let's take a look at this a little bit more, and let's talk about the conservation of mass and how we can obtain mass information from a balanced equation. Let me go ahead and save this quickly. Put this out for us. Okay. All right, so let's go ahead then. Now we did this already, and so I'm not going to spend any more time with this. Okay, but we want to first interpret, in order to obtain masses, what we want to do first is we want to interpret this in terms of moles. Okay, and so just real quick here, just to highlight what we did. Okay, from this balanced equation, then we have 1 mole of nitrogen, 3 moles I'm sorry, of hydrogen, and that will produce 2 moles of ammonia. Okay, and so that's what we have there. And so in the previous example, we were able to calculate then for the masses here. So I'm not going to do that again. Please take a look at that. Okay. But what I'd like to do then is let's take a look at what happens. Sorry. Okay. When you change, if we have to change it. Okay. But so what we're going to do then is I'm sorry, running out of time. What I'd like to do tomorrow is I want to finish up this discussion of masses and how we can obtain masses from the balanced equation here. Okay. And then what I want to do is I want to talk about how we can measure out volumes. Because like I pointed out to you just now, measure out, these are all gases. Trying to weigh out gases, very difficult. It's not an easy thing to do. However, we can obtain volumes that's a little bit more efficient. And so what I'd like to do then is talk about how we can get from a balanced equation information about volumes as well. Okay, so we'll go ahead and we'll continue with this tomorrow. And then again, if you have any questions, folks, please come by after school today, 1:30 to 2:30 to get your questions answered. Okay, if not, I will see you folks tomorrow.